Log on, tune in, find out. Another good idea from Cambridge.
Of today, the first speaker is Professor Brian Davies from King's College London, and he's going to talk on the Ambarzumyan theorem or something like that.
Yes. I'm sorry, I've got my advertisement here. This is about the Journal of Spectral Theory, which has recently been founded, of which I'm the chief editor. You can easily find it by Google by typing in Journal of Spectral Theory. And if you look at the list of editors, you will conclude that this is going to be a very high quality journal, which it is. Okay, so let's get back to the talk. This is an inverse spectral theory of Ambarzumyan. Well, that's the spelling I'm choosing. It's not the only spelling, of course. And this dates back to 1929. I actually learnt about this in a previous I&I meeting on spectral theory of graphs. So I'm very pleased to be able to come to an ostensibly different, well, no, an actually different I&I meeting and tell you that I actually found a solution to a problem which seemed to be obvious from one of the talks. But I'll explain that later, and thank both the organisers of both meetings, which Malcolm Brown might be among both groups. So I thank him doubly for enabling me to come to both occasions. Okay, I don't know which order these things are going to come up, but I don't need to tell you about what self-adjoint operators are, but all the self-adjoint operators in this talk are going to have a discrete spectrum. That is, they're going to have a complete orthonormal set of eigenvectors.
So they're bound?
No, unbounded.
You say for F,
Yeah. For all appropriate F in L2. I hope this is the only mistake which is pointed out, but I'm sure it won't be. They're unbounded. Some of them are compact. Maybe it's the resultant is of the type you said. Okay, so the actual theorem from 1929 refers to the one-dimensional Laplacian minus d squared by the x squared on a finite interval AB. It's very important that this operator is given Neumann boundary conditions. And you're comparing two different operators, one of which is the Laplacian, and the other of which you add on a potential, which, well, to make life easy, I'm going to make to be a bounded measurable potential. So the new operator has the same domain as the old operator, and is given by the second formula here. And the theorem of Ambarzumyan said that if these two operators have the same list of eigenvalues, including multiplicities, of course, then the potential is identically zero. Now, this is not a typical inverse spectral theorem, because normally you need to know that some extra information. For example, you might need to know that if you have two potentials, that the operators have the same eigenvalues for two different sets of boundary conditions. But in this particular case, because you happen to have chosen the Neumann boundary conditions and one of the potentials to be identically zero, it turns out that the simplest possible result is actually true. If the operator with the potential has exactly the same eigenvalues, then the potential is zero. Now, I'm going to prove far more than that, but this will come in a moment. The history of this is given by the first bullet point here, that in the last I&I meeting I went to, two people, Law and Yanagida, were extending this from the case of an interval to a tree. That is a finite collection of intervals which were joined together at the ends by means of some appropriate boundary conditions, and if there are any free ends, you had to have Neumann boundary conditions at the free ends, and he managed to prove that for such a finite tree, the Laplacian is also got the same properties as it does for a single interval. Now, that was only for a tree, but in fact it is true. A tree means that there are no closed loops. It's also true for a compact quantum graph. this is one of the results I'm going to be telling you about. That is, you have a finite collection of continuous intervals, and you join the ends together in some way, and you now do allow closed loops. You can even allow two edges to have the same ends if you like, and you just have to require suitable conditions which replace or the analogues of the Neumann boundary conditions for a single interval. But the proof that I developed actually applies in much more generality than this. It applies to any compact Riemannian manifold. Now, if the manifold, where you're looking at the Laplace-Beltrami operator of the manifold, if the manifold has no boundary, then of course you just initially define it on C infinity functions on the compact manifold, and it's then essentially self-adjoint, and it has discrete, the closure has discrete spectrum. If there is a boundary to the manifold, then you put Neumann boundary conditions on the boundary. I'm assuming the boundary isn't too irregular. I mean, for example, the boundary could be Lipschitz, and this argument will work. And as a final observation, this theory even works for finite combinatorial graphs, where you use a difference Laplacian. But I'm not going to mention that at all, because once you have the idea of how you're doing it, it's actually a lot simpler, because you don't have to go through all the technical complications of the continuous case. And the final point is that you don't even need to assume that the two operators have the same list of eigenvalues. You only need to assume that when you take the eigenvalues of the operator which does have a potential, h, that these are less than or equal to the eigenvalues of the operator which has no potential, plus one extra condition. I mean, obviously that by itself couldn't be enough, because the potential might be just -1 everywhere, in which case all the eigenvalues decrease by 1. So you couldn't possibly conclude that if the eigenvalues of the perturbed operator are less than or equal to the eigenvalues of the unperturbed operator, then the two are equal. But there's one extra condition, which is we'll get to as well. So it's a much more general context, and it's actually a much weaker hypothesis, but the same conclusion. I can't possibly do everything, but I will sort of try to give you some idea of why this is true. I'm afraid this is a very limited result. I mean, it uses all of the special properties, and in particular the fact that you're using Neumann boundary conditions in a very specific way, and I can't see how to extend this to any problem other than this problem. But there we are. So I'm going to be using heat trace asymptotic methods. And once I mean, this has not been something that's been used for this particular problem before, but if you're very familiar with what you can do with heat trace asymptotics, then it somehow seems to be right from the beginning almost certain that you will be able to get something good out of it. So we have this operator h, which is the perturbed Laplacian, and you're looking at trace of e to the minus ht, where t is positive. Now we're looking at in infinite dimensions, so you can take any complete orthonormal basis, you get an infinite matrix. The trace is the sum of the diagonal elements, as written down in the first equation up there. I don't know how is that. Yeah, right, in the first equation up there. And now there's a huge amount known about the asymptotics of this heat trace for small t. And there's under certain conditions there's an infinite order expansion of this type, where typically d is the dimension of whatever it is you're looking at. But effectively I'm going to be using this, but I only need to have some information about a0 and a1 here. I don't need to develop a complete asymptotic expansion. Now, if the two operators have the same eigenvalues, then the trace of the two e to the minus ht and e to the minus h0t are exactly the same. That means that all the constants a0, a1, etc. are exactly the same, and that gives you more or less a moral certainty that you can find out what the potential is, because all of these constants are going to depend on the potential. So you have an infinite number of constants. Of course, you might say, well, you might need some extra information like norming constants as well, but I'm not going to need anything except the first two coefficients. And I've got to set things up in a way that it will apply to quantum graphs and to manifolds with Lipschitz boundaries, not just smooth boundaries, in order to get the result that I want. Okay. So let's say a little bit about the classical heat equation, just to get ourselves in the right mood about heat kernels. In one dimension, the heat equation is written down above, and the solution is very well known, and the heat kernel is also very well known. So in the case that we're looking at, we're always looking at second order elliptic operators, and there's a general fact that when you have second order integral elliptic differential operators, e to the minus ht has a heat kernel, which is non-negative and frequently everywhere positive, and that it can be expanded in terms of the eigenfunctions. Phi n are the eigenfunctions of h, and lambda n are the associated eigenvalues, and you have an expansion of this type, which in good cases is actually uniformly convergent for all positive t. The trace of the heat kernel, well, I said you take an infinite matrix and add up the diagonal elements, but you can also take the heat kernel, and the analogous thing is to integrate the heat kernel over the diagonal, and this gives you the sum of the exponentials of the eigenvalues. I mean, this is all very standard in the subject, but sorry, I don't know what all your backgrounds are. In fact, everything I'm going to tell you is very standard in the subject, but I need to go through it. So, yes, because the operator is real, the heat kernel is real. It's actually pointwise positive, and then you can choose the eigenfunctions all to be real. I mean, if they're not, each eigenfunction, you can take the real and the imaginary part, and you can, if an eigenvalue has got higher multiplicity, then you take the real and imaginary parts, and they are also eigenfunctions. So you can always produce an orthonormal basis in which the eigenfunctions are all real. Okay, so the strategy is as follows. First of all, I have to make some abstract hypotheses about the unperturbed heat kernel. And I've got to use some routine arguments in the field to deduce similar properties for the perturbed heat kernel. That is the heat kernel for the operator which includes the potential. And then after some rather sort of technically heavy calculations, you eventually draw the not very thrilling conclusion that the integral of the potential is less than or equal to 0. That's all I need from that aspect of the work. And then a completely separate argument says that, well, if you know that the integral of the potential is less than or equal to 0, then it can be seen by variational methods that the potential is in fact identically 0. And then, of course, to make any use, I have to have checked that that the abstract hypotheses about the heat kernel are actually valid in all the cases which I told you about at the beginning. And I'm afraid I'm not going to be able to do that because there isn't time and it just takes too much effort. But the fact that the hypotheses I write down are valid in the examples I just mentioned is again something which is standard in the subject. Okay, so what are the hypotheses? First of all, that the operator e to the minus ht has a non-negative integral kernel which is continuous. Now, this is because the operator is a second order elliptic differential operator. That imposes regularity conditions on the kernel by the ellipticity, and that's where the continuity comes from. And because it's second order rather than some other order, it makes the heat kernel pointwise non-negative. And in assuming that the object that you're looking at, the graph or the manifold or whatever, is connected, actually the heat kernel is pointwise strictly positive everywhere. Right. Next hypothesis, that the heat kernel has an upper bound which is given for small t by ct to the minus d over 2. Typically d is the dimension of the object you're looking at, but in order to prove this, I mean, it might not seem very obvious why this should be true. There is a general theorem which is known since the 1980s that a bound of this type is actually equivalent to a certain type of Sobolev inequality, at least if the dimension is at least 3. And that Sobolev inequality can be verified directly from the definition of the operator h or h0. We don't want to restrict to the dimension being greater than or equal to 3, but then there's also a trick which you can deal with the cases 1 and 2 by converting them into the three-dimensional case. For example, if you have a one-dimensional object, you multiply it by itself 3 times, and it becomes a three-dimensional object. Then you get the heat kernel bound for the three-dimensional object, but the heat kernel for the three-dimensional object is just a product of 3 copies of the one-dimensional object. So you get back to the one-dimensional result. That is provable by standard Sobolev inequalities for the quadratic form domain of the operator. And we need to use the quadratic form domain if you want to look at boundaries which are Sobolev, Lipschitz rather than smooth. You don't know what the operator domain is, but you do know what the quadratic form domain is. Next thing is that the smallest eigenvalue of the unperturbed operator is 0 and has multiplicity 1. Corresponding eigenfunction is the volume of the set to the minus a half. I mean, that uses the fact that we decided to adopt Neumann boundary conditions for the unperturbed operator H0. And this is absolutely crucial. So 0 is an eigenvalue, it has multiplicity 1 because the manifold, I'm assuming it has multiplicity 1, but that is regularly proved from the assumption that the set that you're looking at is connected. And finally, I'm assuming that if you eliminate a null set, n, that the heat kernel asymptotics can be written down exactly. It is of order t to the minus d over 2. Well, H2 says that. But if you multiply by t to the plus d over 2, then there is a limit which is independent of the point. But there may be an exceptional set. Now, in the case of a quantum graph, the exceptional points are the vertices where edges join each other. In the case of a compact Riemannian manifold which has a boundary, then the exceptional set is the boundary of that manifold. I think perhaps I should explain why there should be an exceptional set by a very simple example which actually doesn't satisfy these conditions because it's not compact, but here it is. If you look at minus Laplacian in the half line, north infinity, putting Neumann boundary conditions at the origin, then the reflection principle tells you that the heat kernel is given by the standard heat kernel here, plus a component which is associated with the reflection. Now, if you let t goes to 0, you can, if you put x equals y, and look at the first term, if x equals y, x minus y squared is 0, so that exponential becomes 1, and you just get an exact 4 pi t to the minus a half. When you multiply by t to the plus a half, the limit is, the constant you get is 4 pi to the minus a half. But let's look at the other term. If you put x equals y, you get e to the minus x squared over t here, and as t gets smaller, this vanishes exponentially fast. So it appears that the constant is 4 pi to the minus a half for all points. However, that's not true if x equals y equals 0. If you had x equals y equals 0, then this term, this exponential coefficient vanishes too, and this is 1, and the coefficient at the boundary is twice as big as it should be. I mean, this reflects a discontinuity between the two, interchanging the two limits, where x equals y goes to 0 and t goes to 0. You can't interchange those. So we have to accept that boundary points subject to Neumann boundary conditions are going to have different asymptotic behavior for small t. Why does this not worry you? Because in the end, I'm going to be using the Lebesgue dominated convergence theorem to prove that a certain integral has a certain form in the asymptotic limit t goes to 0, and if there's an exceptional null set, this doesn't make any difference to the dominated convergence theorem. I've got till 12, I think. Yes? Okay. So there's my second mistake. The constant in H4 in this example is not 1 and 2, it's 4 pi to the minus a half and twice 4 pi to the minus a half. So I'm up to 2 so far. Okay, so now this statement is not quite correctly made. There is an equivalence between two statements. One is that the heat kernel is continuous with respect to t, x, and y, at least provided t is positive. And the other is the statement that the eigenfunctions are all continuous and this series converges uniformly for all t greater than 0. Now, one way, I'm not going to do it either way around, but this is hardly surprising. Stating that the heat kernel is continuous implies more or less directly that e to the minus ht maps L2 functions to continuous functions. If you put an eigenfunction in there, you apply e to the minus ht to an eigenfunction, you just get a constant multiple of that eigenfunction. So the eigenfunction will be continuous. But you actually end up also with bounds on the uniform norm of the continuous function, which shows that this series is converging uniformly. In fact, uniformly in x, y, and t, provided t is bounded away from 0. So we've got this uniform convergence to deal with, and actually that's quite useful. Well, I haven't written it down, but if you now calculate the trace of this, then you put x equals y and integrate, then you see that you have phi n of x squared. If the eigenfunctions are normalized, you integrate that with respect to x, you get 1, and you get just the sum of the exponentials of the eigenvalues. So we're looking at the sums of the exponentials of the eigenvalues whenever we look at the diagonal behavior of the heat kernel. Okay, now this is a little bit more difficult. First of all, the formula at the top, remember h is the perturbed operator, which is equal to h0 plus v. Even if you are looking at n by n matrices, this top formula is then, I think, called Lee's formula, but proving that it's valid even in the case of non-negative self-adjoint operators is often called the Trotter-Lee formula, but in the case of quadratic forms, which actually isn't needed, it's actually due to Kato. This top formula is true in very great generality. I want to look at certain inequalities which you can draw from it. And these are slightly unconventional. I want to talk about one operator being less than or equal to another if the kernel of the first operator is pointwise less than or equal to the kernel of the second operator. So I'm not talking about inequality in the sense of spectral inequality. In other words, the difference of the two operators being having non-negative spectrum. I'm talking about pointwise inequalities of the relevant heat kernels. You will see this is again a standard technique for positivity preserving operators, and you see that you can immediately draw a conclusion that is written down here by the following trick. If you replace this potential, which is of course multiplying by a diagonal function, by the maximum value that it can have, then the maximum value this can have will be e to the infinity norm of v times t over n in there. But that's a constant. And so you can take it out and it was raised to the nth power, so you just get that. The other, what remains here, is a positivity preserving operator with a t over n, which is raised to the nth power. So when you multiply that out, you get this term. And if instead of taking the maximum value that this can have, you take the minimum value this can have, you get the other thing. Now that simply tells you that if you know something about the kernel of e to the minus h0t, then the kernel of e to the ht is of the same order of magnitude, pointwise. And that's true for all t greater than 0, and so enables you to look at the certain asymptotic limits and be able to control them. Now this is not quite enough to imply that the eigenfunctions of h are continuous. One needs to do some more work than that, but it does enable you to imply that h has discrete spectrum, if it were not obvious that this is true anyway, which it is. And so you get this bound on the heat kernel of the perturbed operator, which means that the heat kernel of the perturbed operator has some of the same properties as the one for the unperturbed operator. Now, that's one way of finding out information about the perturbed operator from information about the unperturbed operator. There is another way, which goes by all sorts of names, and it depends how much of a mathematician or a physicist you are, but this is to look at e to the minus ht, e to the minus ht, and expand it as an infinite series in a potential. So there's the term which doesn't involve the potential, which is here, then the term which involves the potential linearly, which is here, and then the term which involves the potential quadratically, which is almost here, if you don't look at it too closely, and maybe if you're at the back you can't look at it too closely. And then I seem to have left out the terms in the infinite perturbation expansion, which are third order, fourth order, and so on. And it's well known that this infinite series converges in all possible senses. It converges in operator norm, the heat kernels converge uniformly, and they give the same answer, of course. I mean, everything works the way you would like it to. But I haven't written down an infinite expansion. I've written down just 3 terms, the zero order term, the first order term, and the second order term, until you notice that in the middle here, I haven't put h0, I've put h. So what you actually do is you take the infinite order expansion, you take all the terms from the second one up, and you recombine them to get this. Now, the point is that this final term, all we need is a crude estimate of its magnitude. And we can use the bound that we have just proved by the other method for the heat kernel of this term in the middle. So we don't need to know terribly much about the term in the middle, except for its basic order of magnitude, in order to be able to conclude that this final term is irrelevant asymptotically as t goes to 0. Okay, so I mean, this is again a standard bit of stuff, but it's got to be written out under the suitable axioms so that you can use it in the contexts that we want. Now, not only does this converge in operator norm, in Hilbert-Schmidt norm, in uniform norm, but also converges in trace norm. And so you can take the trace of every term in it and you get an expansion. Now these two are obvious. This one is obtained by looking at the trace of what I was calling A of t, and the rho of t over here I only need an order of magnitude of is obtained by taking the trace of B of t. But let me explain rather what happens when you take the trace of A of t. It's well known that the trace of a product doesn't depend on the order in which you take the product, and so in here I can remove the e to the minus h0s from the right hand side to the left hand side after taking traces, and then I can multiply it by the other term and you get e to the minus h0t, which does not depend upon the variable of integration, and so you just have simply e to the minus h0t and then v, a trace, and then you multiply by the length of the interval, which is t. So that's what I've written down. Here is the length of the interval, and here is the trace of the product written down as an integral along the diagonal of the relevant operator. I've got a minus there because there was a minus in the previous equation, because eventually there's a minus up here, that has a minus, and that one should have a plus. As far as this term is concerned, we have to calculate the trace of this lot, and we know the order of magnitude of these 3 heat kernels. We know that the region you're integrating over is a triangle whose volume is t squared over 2, and so you know what the order of magnitude is, and you get here a 2 from the volume being 2, and you get a minus d over 2 from the fact that you can control the size of all the heat kernels. And that should be compared with this term, where kt0t is of order t to the minus d over 2. So this term is order t to the 1 minus d over 2, whereas the remainder is of order t to the minus 2 minus d over 2, which is negligible asymptotically by comparison as t goes to 0. Okay, so that really is the formula out of which I'm going to get remarkably little, but enough to go on to the next stage. So the conclusion is that the integral of v is less than or equal to 0, provided the eigenvalues of h are all smaller than or equal to those of h0. This follows remarkably easily. The point is that if h has smaller eigenvalues, then the left-hand side is bigger than the first term on the right-hand side. And so all the other terms on the right-hand side collectively are positive. But this term, the final term, is negligible as t goes to 0 by comparison with this term. So this term, having a minus, this term is asymptotically negative as t goes to 0 after you've put in the appropriate compensating factor, which is t to the d over 2 minus 1. Well, we can actually look at the asymptotic behavior of the integral. The point is that v is bounded, the region is bounded, and the heat kernel on the diagonal has a limit which is independent of x almost everywhere. Remember, there was an exceptional null set, but off that null set, after multiplying by t to the plus d over 2, this is uniformly bounded. It converges to a constant independent of x, except on a null set. And so that integral, the asymptotic behavior of that integral can be evaluated, and you end up with the conclusion. So that depends absolutely upon knowing not only a uniform bound for all x, but also an exact formula for almost all x. It could be also developed, if you wanted, to allow v, at least as far as this part is concerned, v could be L1 rather than bounded. So I mean, I'm not going to the limits of the technique which you could use. So that's the conclusion that you get out of that. And now I can abandon this technology completely and go on to the completely different and much, well, in some senses much simpler, but slightly more tricky ideas, getting the desired conclusion. So the hypothesis now is that the eigenvalues of h are all smaller than or equal to those of h0, but also that the smallest eigenvalue of h is 0. So this stops us simply having v constantly minus 1 and just reducing all the eigenvalues by 1. So all the eigenvalues except the smallest can decrease, but the smallest eigenvalue must remain 0. And from that you conclude that the potential is identically 0, and therefore, of course, all the eigenvalues are equal. Okay. Now, at this point, I need to actually draw some pictures. I've never mastered the technique of producing pictures for presentations painlessly. I mean, I can do it painfully, but there must be a painless method, since other people seem to manage to, or maybe other people are just more determined than I am. So I'm going to now convert to using a blackboard. So I want to look at the smallest eigenvalue, f of s, of this operator h0 plus sv, where s is real. We're only really interested in two cases, s equals 0 and s equals 1. But in order to do this, I need to look at the whole range of s's and gradually build up a picture which will show you eventually that f must be identically 0. So let's have a picture like this. Here's s, here's f of s, and here's 1. Now, if you put s equals 0, then you're looking at the unperturbed operator. It's got Neumann boundary conditions, and so at that point it vanishes. Hope that's big enough for people to see. I mean, I couldn't, but you know, most people's eyesight is better than mine. I'll turn this around. In the hypothesis of the theorem, I'm assuming that for s equals 1, this function also vanishes. So there are 2 points on the graph. The next thing is that this function is concave. Well, there is a standard variational calculation of the bottom eigenvalue of a non-negative self-adjoint operator. It's given by this formula. You take, well, in general, the bottom of the spectrum is the inf, but since we are looking at operators which all have discrete spectrum, actually you can take min instead. And so the bottom eigenvalue as s varies is given by that minimum. Now, if you look at each expression for each s on the right-hand side, it's a linear function of s. So you're taking the minimum of a family of linear functions, and that's going to give you a concave function. You expect something roughly like that. I've got a duster here, so I can change it as we get more information. The next thing is that this function is an analytic function of s. The reason is that we're dealing with second order elliptic operators. We know something about, well, hypothesis 3 says that the smallest eigenvalue has multiplicity 1 for all values of s, and then there's a general theorem which has got nothing to do with ellipticity or anything else, which says that if you have a non-degenerate eigenvalue of an operator which depends analytically on a parameter, then the eigenvalue also depends analytically on a parameter. So I don't need to alter this diagram now. This is an analytic function from this point onwards. But the next thing is really rather important. It's not just that we know something about the function at the 2 points. We also know that the derivative at 0 is less than or equal to 0. Now, why? If you have any operator plus SV and the eigenvalue is f of s, then f dash of 0 is equal to the perturbation applied to the eigenfunction associated with the unperturbed operator. I'll call that phi sub 0, phi sub 0. Phi sub 0 for 2 reasons. First of all, it's the eigenfunction for the smallest eigenvalue of the unperturbed operator. And secondly, it is the unperturbed operator which you apply it to. So that's a general formula for how the eigenvalue, bottom eigenvalue, or any eigenvalue changes when you put on a very small perturbation. Now, the point here is that the unperturbed eigenvalue, the unperturbed operator has Neumann boundary conditions, and I put into H3 the requirement that phi 0 was equal to mod x to the minus a half, which is constant. And if it wasn't for this, I would not have done anything worthwhile at all, because that means when you integrate this against this, this is the same as mod x to the minus 1 times the integral over x of v of x dx, and that's less than or equal to 0. So you have this magic coincidence that you have proved in the first part that the integral of v is less than or equal to 0, which might be true in more generality, but it's only useful because the eigenfunction of the unperturbed operator is constant, and that's only true under Neumann boundary conditions. So we have this analytic concave function whose slope at this point is less than or equal to 0, but it goes through that point. Now, if the derivative was less than 0, you would have to go down there. So its derivative must be equal to 0, and it's concave, so it actually has to go right across like this. The only concave function which has 0 there and there, and which has derivative at that point which is less than or equal to 0, is constant. And that doesn't use the analyticity. That only uses concavity. But now I can use the third conclusion. It's an analytic function. So not only is it 0 here, it's 0 over the whole real line. Now, finally, if the potential were negative anywhere at all, I mean, then we could take a little test function which had support in where the potential was negative, and then if you go back to this step here, so if v is negative somewhere, and if phi has support where v is negative, then you can see that by making s positive and large enough, this thing becomes negative. But because it's analytic, it's 0 everywhere. So v can't be negative anywhere. And if v can't be negative anywhere, but its integral is less than or equal to 0, it can't be positive anywhere either. And so it must be 0. So there you are. Now, I've got 4 minutes left, but I don't know I've got anything much more to tell you. I mean, what you can see is that this whole approach has sort of 2 aspects. One is using the asymptotic expansion of heat kernels. Now, this technique, I don't know how far it goes back, but it became very prominent in the late 60s in the context of the Atiyah-Singer index theorem, and also in the context, I'm not sure quite when it was. Oh, yes, yes. But this.
Think of the century, previous centuries, a couple of Indians, so that's
but in particular, the idea that one should get infinite order asymptotic expansions of the, as t goes to 0 of the trace of the heat kernel became very prominent in the context of the Atiyah-Singer index theorem, and also in the context of Mark Katz's later conjecture that the eigenvalues of an operator of a Laplacian on a bounded plane region might determine the shape of the region. Now that was actually turned out to be false, but in the course of attempting to prove it, a huge amount of work was put into actually understanding what these coefficients in the asymptotic expansion of the heat trace were. So I mean, this technology is very, very well developed, but most of the work that's been done is basically is going too far, perhaps. A lot of the work which has been done has been assuming that the regions, the manifolds concerned, had smooth boundaries. Actually, everything I've told you here will work for a Riemannian manifold which has a Lipschitz metric and a Lipschitz boundary, provided you apply Neumann boundary conditions. So the heat kernel asymptotic stuff is, I mean, there's vast amounts of literature on it, and it was one of the fields which I also did work on in the mid-late 80s, showing that some of the results could be extended to operators with which didn't have smooth coefficients. The second aspect of this work, the final steps, I mean, it's just a series of tricks which just all happen to fit together. It's a matter of enormous good fortune, and I mean, you can see that one of the critical factors is that you know that the integral of v is less than or equal to 0 by a general argument, but that's only useful because that integral of v is essentially the same as the quantity which is used in first order perturbation theory, and that would not be the case unless you started off with Neumann boundary conditions. I'd love to think that this whole proof could be used to obtain far more inverse spectral results than I have obtained, but I can't see how to do so. It only applies to second order operators because of the use of positivity preserving kernels everywhere. It only applies to Neumann boundary conditions for this reason, and it only applies to second order operators also because the bottom eigenvalue, even of a fourth order operator, can be degenerate. And of course, if you had got a fourth order operator, which if you prove by some modification of my ideas that it was constant on this interval, it might well have a completely different form above that interval, because you simply do not have non-degeneracy of the bottom eigenvalue, even for some quite simple fourth order biharmonic operators on simple plane domains. So the whole thing seems to be a bag of standard tricks which happen to all fit together beautifully for this particular problem, and take it to a very great level of generality. But I'd love to say, perhaps you could extend this to a lot of further problems, but I don't see how. So I'm afraid at this stage I'm pleased to thank you for coming and listening, and hope that you feel you've got something out of it.
Questions?
Well, in the remainder, you have 2 minus d over 2.
Yes.
So this means that d is 1.
No, I probably didn't explain this as well as I could have.
You did.
Here's the equation.
First
Right.
was t.
Right, so probably it's easiest to multiply everything in sight by t to the d over 2 by 1. So times t to the d over 2 minus 1 on every term on both
I
sides.
understand this. From k naught you get another.
Yes. So then, if you do that, then this becomes of order 1. This becomes of order t. These things, you don't need to know what size they are. All you need to know is that this one is bigger than that one.
I made a mistake here.
No, you're not the only person who's not understood what that particular step in the argument. So you really should be multiplying everything in that by this before taking the t go to 0 limit.
Any other questions? Let's thank Brian again.